Okay, so thank you. So my talk is on distributed computing, okay? So I spend my research life on working on distributed computing, and I will take the simplest problem we have to address in distributed computing, okay? So before, I like a lot this slide. It's not from me. So it's a mother with her son, okay? And she answered, no, you were not download, you were born, okay? So I think there are more and more applications, but we never have to forget that science and technology is a work of human being, okay? And up to now, we still are not machine, okay? Maybe the future will be connected to machine, etc. But we have maybe the last people, okay, that have some full freedom. We are not connected in our mind, okay? Okay, so informatics actually is a merge of science and technology, okay? It's not only technology, it's not only science, it's a merge. And so there is a famous joke, maybe you know this joke. Do you know what is the difference between science and technology, okay? So the joke is, science is what the parents teach their children, okay? And technology is what the children teach their parents, okay? And a lot of, in my case now, okay, when I have some problem, I always asking a PhD student to solve. The problem is solved immediately, okay? So that's the difference between science and technology. So there is something that is, some people are saying theory is useless, okay? It's useless, I need application, only application, okay? Of course, that's not my view, and the problem is that incorrect program, okay, can give rise to very strong disaster, okay, very, very strong disaster. I don't know, what is a car? What is a car? What is a plane? A car today is a distributed system, okay, in a synchronous with synchrony, okay, and with a lot of devices. What is a plane? A plane is a distributed system with a lot of devices, okay? So the software today, if in a plane or a car, is more expensive than the rest of the car, okay? And the difference, there is a big difference today, is that the software in a plane, at least for Airbus, I'm sure, has been proven correct, okay? And I don't know a car whose software has been proved correct, okay? So that's a real problem, practical problem, okay? So some problem, so the problem, we need to know that I give you assumption, okay? What sometimes we call a computation model. I give you some assumption, and I ask you, can you solve this problem assuming the assumptions are satisfied, okay? And in some cases, the answer is yes. In some cases, the answer is that's impossible. And so we need to know, okay, with the weakest assumption as possible, if a problem can be solved or not, okay? So in distributed computing, you have two major problems. One simple, the other one is more involved, is how to implement a variable, okay, in a message passing system in which there are failure. And the other one is how to agree in a distributed system in which there are failures. That's a famous consensus problem, okay? And when a problem cannot be solved, which are the additional assumptions I need to add, okay, in order the problem becomes solvable, okay? So, what is a distributed system? A distributed system is a set of computed entities. You can call that process, node, whatever the name, and they need to cooperate. If you don't need to cooperate, it's not distributed, of course. And you have a communication medium to cooperate. So you have either read-write register or variable, multicore, okay, multicore, and message passing, okay, another way to operate, or both. It can be hybrid, okay, you can have cluster sharing a multicore, and now the cluster communicate using message passing, okay? And this is done in the presence of adversary. So we have adversary, what we call adversary. Adversary is the possibility of failure, okay? And you have two important types of failure. As soon as the computing entities are concerned, one is a crash. a process is executing correctly, and after some time, it crashes. So it stops executing forever, okay? That's a kind of failure. And another kind of failure is called Byzantine failure, okay? So this was introduced more than 40 years ago by Leslie Lamport. So what is a process as a Byzantine behavior if it's doing anything, okay? It's not executing the code, it is assumed to follow, okay? For example, I need to send a broadcast my age. As some people, I'm saying 20, at others 30, etc., okay? So I have a Byzantine behavior, okay? And Byzantine behavior, for example, have been popularized by Bitcoin, okay? In Bitcoin, okay, that's very important because if you have people that are dishonest, okay, they are Byzantine processes, okay? And so distributed computing is a science of cooperation, okay? We want to cooperate. As soon as we want to cooperate, we need to follow some rule, okay? And that defines the science of cooperation. So more generally, so distributed computing arises when you have to solve a problem in terms of entities, so process, agent, peers, actor, processor, whatever the name, such as each entity has only a partial knowledge of the input parameter. So you have a part of the input parameter, I don't know them, I have an input of the input parameter, no one knows them, okay? Each of us, and we have to solve a problem, okay? So we can define also distributed computing at we have to master cooperation in a world with uncertainty. Uncertainty is created, for example, the system can be synchronous or asynchronous. So synchrony is a very strong assumption, okay? So we have to respect there are bounded delay for message, for example, okay? Or you say, the message are never lost, but there is no bound on the transfer delay for message, okay? So in this case, this creates some uncertainty, and we have to master it. For example, a message can, I don't know that there is no bound on message transfer. I send you a message, maybe it arrives very quickly, and maybe it will arrive in 10 days. Okay, we don't know. So that's a problem for you. And if you don't know if I crash, okay, or if I send a message, the message has not yet arrived. You cannot distinguish both cases. So there is a famous quote by Lamport in 85. He was in an email sent to a colleague, and he said, Leslie Lamport, so Leslie Lamport is the one of, you have two people from a scientific domain that were the patriarch, okay, the pope of the distributed computing religion, they were Dijkstra and Lamport. Okay? They opened all the problems and they solved many of them. So this famous quote on Lamport is, a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Okay? So it's formulated as a joke, okay? But that definition can be a definition. Okay? And something that is important is today, the world is distributed. We have no choice, okay? So more and more applications are distributed. Okay? When I was a student, a long time ago, in the previous millennium, a very long time ago, okay, main problem were to design operating system, to design compiler and database, okay? A little bit artificial intelligence, okay? Today, distributed computing is very, very important because many applications are distributed. So there is sometimes a confusion between parallel computing and distributed computing, okay? So parallel computing actually is something that is controlled by a programmer, okay? So you control, and what is your aim is to be efficient, okay? For example, I have to sort an array, very simple example. You sort half of the array, I sort the other half, okay, at the same time, in parallel, okay? And then I'm using a fuse, okay, to reconnect the two sub-arrays, okay? So it's my choice as a programmer. Now, in distributed computing, the distribution is imposed. You have no choice. There is a computer in Malaga, there is a computer in New York, there is a computer in, I don't know, in Moscow, one in... one in Japan, etc. And then there is an application that is distributed, is not under my control, is not under control, is imposed to us, okay? And we need to cooperate, okay? So, a few definitions, okay? So, the adversary I consider in this talk are failure and asynchrony. Asynchrony means there is no bound on the speed of processes, okay? And there is no bound on the transfer, delay transfer for messages, okay? And failure. So as I told you, there are crash failure, okay, on one side, and on the other side, the most general failure are Byzantine failure. A process can do anything. It does not respect, okay, the behavior it should. So what can be done, what cannot be done? So if I take two examples, I want to implement a variable, okay, read-write variable on top of a message passing system, so simulate a multicore, okay. This is possible with this assumption, okay, only if a majority of processes never crash in the crash model, okay? So you need to have a majority of processes that never crash, the problem can be solved. If a majority or more processes may crash, the problem cannot be solved. So it's not because you are stupid, you are not enough imagination to have, no, the problem cannot be solved, okay? That's another problem that we know today, the answer, is the very famous problem called consensus. So consensus is a very easy problem to formulate. Each of us, we have a value. I have a value, each of you has a value, okay? And we want to agree, okay, on only one value. Maybe it will be yours, maybe it will be my value, maybe it will be his value, we don't know, okay? So we propose a value, and one value will be decided by all of us, the same value. That is one of the proposed value. If there is no fault, the problem is trivial. We exchange the value and you take the biggest one, by default, okay, for example, and we'll have the same, okay? If with crash failure, okay, the problem is impossible to solve, even if only one process may crash, okay? So the consensus problem was introduced 40 years ago by Lamport, and the impossibility in synchronous system, but in asynchronous system, okay, no bound on message and on speed of processes, the problem is impossible to solve. Okay, I'm repeating, even if one process may crash, okay? So we can say, okay, what to do? So it means that the assumption we are considering are not strong enough to allow us to solve a problem, okay? So there are several ways now that have been done. One is to say, okay, I am assuming the system is synchronous. Okay? Bounded, there are delay for message and speed of processes, and everyone knows the delay. Okay? And the delay are always respected. Then the problem can be solved. Okay? And we also know the minimal synchrony assumption we need. Okay? There is another approach, is to use random numbers. So if we have random numbers in the model, okay, we can access random. And in this case, the problem can be solved, okay? So that's important to be done. And something, so I have to say something also about Bitcoin. Bitcoin is interesting because Bitcoin, okay, he has to solve a consensus problem, okay? We need to agree, the famous puzzle to solve, etc., in Bitcoin. And what is strange is Bitcoin, it was based on consensus, but 2 years ago, it has been shown that to solve the money transfer, okay, this application, so solved by Bitcoin, to solve money transfer, you don't need consensus. Consensus is stronger than necessary, okay? So it has been shown by people at TPFL in Lausanne, and in my research group in Rennes. Okay, we show that that's not, you need only FIFO links. The links have to be first in, first out. That's sufficient. If you have that, you can solve money transfer. So in this talk, I'm interested, I want to show an example. So the example is simple, how to implement on top of a message passing, okay, in which there is no bound, okay, a read-write register. And to simplify, the register can be written only by one process. So everyone can read, but only me can write, okay? That's all. So if you're able to solve this case, then to generalize is not complicated. Okay? So what do we mean? So I show you here as an example. So you have 3 nodes, P1, Pj, and Pk, okay? This one is start reading, it terminates the reading, etc. This one is start writing, it terminates the writing, okay? So what to mean atomic register? Atomic register means that whatever the way it occurs, everything has to appear as if the operation we executed one after the other, okay? Not simultaneously. Okay? For example, here, everything appears as this one, no concurrency, so write. Then this one was reading, so it obtains the value 1. And here you see there are 2 writes, they are concurrent, okay? So in this execution, everything appears as this write occurs first, and then this write occurs after, okay? So, and here the read, of course, read the last value, so everything appears as write 1, okay? Then read 1, then this one, write 3, then write 2, and then read 2 and read 2, okay? So this can be, so that, with an example, the definition of what is an atomic read-write register, or variable, sorry. So I'm repeating, so what we have to implement it, so for example, a set of node, P1, Pi, Pn, and n node, and n, each of us know n. We know n is a variable that is known, okay? So we have a local memory, and we have a network, okay? And we need to design an algorithm, okay? So actually this is nothing, is a peer-to-peer system, okay? Okay? And in a peer-to-peer system is a system in which each node at the same time is a client and a server, okay? That's all. So, just repeating. So processes, they are sequential, asynchronous. The communication, to simplify, I'm assuming the network is complete. I can send a message individually to each of you as internet, okay? So point to point. No bound on transfer delay, but it's finite. It's not in. Then reliable, we are assuming that the communication, there are no loss, no creation of message, no duplication, no alteration. So the network is clean, okay? Point to point is the sense that if you receive a message, you know the name of the process that sends the message, okay? That's it. And the channel are not required to be FIFO, first in, first out. Message can be arrive in any order, okay? So, then the operation offered in the model are, I can send a message, a process PI, or a node PI can send a message to a process PJ, and a process can receive, when it evoke receive, he receives a message, okay? He's blocked until he receives a message, okay? And to simplify the writing, we are using a macro operation broadcast a message, actually, and broadcast message is a shortcut for I send the message to each of you, okay? That's so if I crash during a broadcast, maybe some of you will receive a message and others will not receive a message because I crashed while I was executing broadcast, okay? The broadcast is not reliable, okay? So, just repeating, crash failure, you halt prematurely. Okay? You are correct until the end, if you don't crash, or until you crash if it is the case. So the problem can't be solved if and only if, so let us K denote the number of processes allowed to crash. Okay? So it means that K has to be smaller than n over 2. So the number of processes that are allowed to crash is less than half. There is a solution. Otherwise, there is no solution. It's not, I'm repeating, it's not because you are stupid, unable to design an algorithm. No, there is no solution, okay? And that's important to know when you have a problem. It can be solved or not. And if it cannot be solved, which assumption I need to add, okay? So the assumption is, for n is this one. The number of processes allowed to crash, okay, had to be less than a majority, okay? It has to be smaller than n over 2. So this problem has been solved a long time ago. So asynchrony means that it's impossible for me, if I'm waiting a message from you, okay, to know if you send me a message and the message is very slow, or maybe you crash and so you didn't send a message, okay? That's the difficulty, the main difficulty. So, and this is called the indistinguishability argument, okay? So typical algorithm solving the problem use a very well-known notion, okay, it's nothing new, sequence number, the first message I send you, etc., okay? Then, as soon as we have sequence number, it's similar to say the channel are first in, first out. Notion of quorum, okay, set of node, and intersecting quorum, we are requiring that two quorum intersect, okay? They have at least one process, okay, in the intersection. Then, well-known notion of request, okay, and acknowledgement, okay? And the idea is a write intuitively. In order to be implementable, we need to have a write means that if everything has to occur, if a majority of processes that don't crash receive the value of new write, okay? As soon as the majority of processes has a value the writer wants to write, okay, then it's okay, they can communicate, okay, there's no problem. And copy. So, the algorithm as I described is for single writer, I'm repeating, and everyone can read the register. So the variable, so reg is the name of the variable, okay, we want to build on top of the message passing system. So locally, you have a copy, okay, of the register. So we initialize, all of us will say to bottom, to the same value, okay? We have a copy. Then, WSNIE, for write sequence number at process PI, is a sequence number associated with a value that is in local variable, okay? Actually, and this variable, read sequence number, is a sequence number, okay, of the last read you obtain. I read the value, I obtain the value n is sequence number, so it will be the last one. Initially, it is 0, of course. Okay? So this is very classical, very intuitive. And now there is another variable that is more delicate. SWSNI, it contains a synchronization variable, okay? Synchronization variable for the write with the sequence number. So it contains the sequence number of the most recent value of the register you know, or the variable you know, that to your knowledge, to PI knowledge, it is known by a majority of processes. Okay? You know that the majority of processes know that value. Okay? Actually, what we are solving is a problem of synchronization. Okay? Distributed synchronization. Okay? So you know, so this variable is at the heart of the time-efficient implementation I will introduce. Okay? And a value with this sequence number, okay, will be the value of register in res I. We'll save it in res I. So actually, we need on each node 4 variables, okay? A copy of the variable, value. You need the corresponding sequence number. For you, the last read you did, the sequence number of the last read, and this variable, okay, synchronization W, S, and I, okay, that is crucial to implement the algorithm efficiently. So now on the message side, so you have 3 types of message, okay? Write, you are using message write to disseminate a value for the writer. Read is to disseminate a read request, of course. And state, we'll see, is to ensure the correctness. If you return a value when you read the variable, okay, it is a good one, okay, it's a good value, okay. So we need that. Now, so what is the, so something that is important that makes SALT in distributed computing is the fact a lot of distributed problems to solve, okay? If you count the number of lines you need to solve them is very short. Okay, then, of course, you translate that in your favorite language, okay? But you see, the write operation is 1, 2, 3, 4 lines. Okay, it's not 100 or 1 billion line, okay? But it's subtle. So, when you want to write, so there is only one writer, okay? So the writer is saying it is increasing this variable, okay? One more write. He puts the variable locally in his local variable reg I, and then he sends a message to all write type with the sequence number and the value. And he waits. He waits, okay, until it has received acknowledgement, so identified by this number, okay, from a majority n minus k processes, okay? You remember that k is the maximum number of processes that are allowed to crash, okay? So are sure n minus k processes are correct, they will answer, okay? So here, you will never be blocked, okay? Then, so we send a message right. When you receive, if you receive a message right, okay, from the writer, so it carries a sequence number and a value. So this is, if it is a new value, the constant number you receive is greater than the copy you have at your node, okay? What you do, you update the new value, and the last sequence number is this one, okay? And then, if this has not yet been done, you forward the message you receive, okay? Why you need to forward the message? For a very simple reason. Maybe the sender crashed in the middle of the broadcast, some correct received, the other didn't receive, okay? So actually, you play the role of the writer, okay, just in case. So, and additionally, control part, then if this message is received from n minus k processes, okay, the maximum, you are sure that now the value is safe. It has been received at the maximum number of processes for which you can be sure, okay, they have a copy of the value you just received, okay. So in that case, well, I'm skipping this one. And then you update, okay, you update that to your local variable, okay, reg si for the read. So this is for the write, and this is for the read. You want to read next time also a correct value. Now, when a read operation you see is 1, 2, 3, 4, 5 lines, okay? So it's not the number of lines that makes things complicated, okay? It's the fact it is distributed that makes the work difficult to follow. So you say receive sequence number as 1, okay, when you want to read, and you say I want the value, okay, and my request, the sequence number of my request is this one, okay? maybe I send all requests, okay, that are still traveling, I don't know. And then you wait. You wait until you have received message corresponding to this one, okay, okay, from n-k processes. So you wait enough, okay, to be sure that, to be able you to exploit the value you have, okay, enough other processes know the value, okay. There is no confusion, okay. So it's realized by this text, by this wait. And finally, you return. So I don't want to enter into the detail. I'm just repeating that you have algorithms that are complicated, difficult to understand, okay? Because in the sequential world, things are very easy, okay? If the program is correct to this point, it is correct. It is correct. At least you can have confidence on this part of the program. Here, we don't know. So we need to cooperate. So now the efficiency, because from an engineering point of view, that's very important. So if you assume that local computation time is 0, local computation take no time, only message take time. And let us assume that the transit time of a message, the delay, round trip delay is delta. So the round trip is 2 delta, okay? So in this case, the number of write operation take at most 2 delta time unit, okay? And then the read operation that occur when there is no write, it takes also 2 delta. Okay? And then it will depend if there is concurrency when I'm reading, the writer is writing, okay? In this case, it can take more, okay? 3 delta. And if the writer is crashing while you want to read, it can take until 4 delta, okay? So it means that the algorithm is pretty good for one read-dominating application. When you have a lot of read and very few write, okay, it's very efficient. So now, if you want to go from single writer to multi-writer, so this is not complicated at all. Actually, you need to replace that's a classical technique, you need to replace the sequence number by a Lamport timestamp, okay? A Lamport timestamp, I don't know if you are familiar with Lamport clocks. So you replace, so is a pair with process identity, your identity, and a logical date. So when you receive a date, you always update the last date, the last value I receive, then I do always taking the maximum, okay? In this one. And comparisons, very classic, people working in mathematics, that's a very, very classical technique, okay? So, you have more algorithm. You could ask, for example, okay, we know the problem can be solved, I'm repeating, if we assume that a majority of processes is correct. There are this algorithm or other algorithm. Now, you could say, I need to, in message, the message carry a lot of things, okay? For example, when you send a write, okay, you broadcast a message, and it carries 2 things, okay? This is the value. So the value depends on the application. It does not depend on us, okay? But the control part we are adding in order to have a solution, sequence number, etc. Is it possible to have less than sequence number? Information, okay? You can say, okay, sequence number can increase forever, 1 billion, okay, 1 terabillion, etc. No. So is it possible to have, to bound, okay, this information? So it has been shown. So it has been shown in now in 2016, okay? Actually, you can reduce the control information to 2 bits. So each message carries the value that is written, okay, and 2 bits of control. Of course, so if that's possible. It means that the algorithm doing that, at each node, you need to keep more information than before, okay? And then, okay, so now the case of Byzantine processes. So actually, Byzantine processes, so it's possible, but it's possible only if two conditions. We are n process, n node, okay, so there is one register per node. There is a register, I'm the only person that can write it. You have your register, you are the only one that can write it, okay? So it's called single writer, multi-reader. And in this case, why? Because if we share the same, and one of us is Byzantine, he can write bad value in all the register, okay? So it will be meaningless, okay? So that's possible, but it's possible if n, the number of nodes, is greater than 3k, or k is the maximum of processes that can be faulty, that can be Byzantine, okay? Otherwise, it's not possible, okay? Okay, so I will stop here. So I don't know, so it was a quick overview of read-write algorithm in asynchronous system. I presented what is distributed computing and distributed system, distributed application. And of course, if you are interested, there is a very, very nice book, okay, fault-tolerant message passing distributed algorithm. So you have a part of the book, okay, that is on reliable broadcast. So the reliable broadcast is a primitive you need to build in any distributed system to be able to disseminate information, to broadcast a value despite adversary, okay? That's very important. Okay, bon, read register and agreement problem, also consensus and all the stuff, consensus, synchronous and asynchronous problem, okay? And for people that are addicted, you also have this book on, so this book, message passing without fault, no failure. No failure, a lot of all the classical problem, and this one is a read-write. So the communication model that is considered is read-write, no message passing, only read-write. Okay, so you have a classical shared memory, a multi-core, for example, and you want to solve distributed problem on top of a multi-core. Okay, so that's all. Thank you.